Okay, let's first draw a little function machine for f. I love these function machines. X's go in, f of x's come out, yeah? Okay. So let's suppose I've got all of these, and this is pretty similar to that problem we just did. I know the output. I want to find the input that created it. Okay? So I've got all these outputs, and I need to know what inputs caused them to happen. So our method is going to be creating a new function that takes f of x's as inputs and spits out x's. Okay? And we call this the inverse of the function f, or f inverse. Now that's the notation we use, an f with a little -1 as the superscript. Does that mean taking the function f and raising it to the -1st power? No, that is just notation. Okay, that means inverse. Am I allowed to raise a function to the -1st power? Absolutely, it would just look like this. You take the whole function raised to the -1st. If you're writing that little -1 next to the name of the function, you're representing its inverse function, not its reciprocal. Okay? Sine has an inverse function. We call it arcsine. It also has a reciprocal function. We call it cosecant. Cosecant and arcsine are completely different functions. We'll learn all about those this year. Okay? Why do we need inverse functions? Well, let's think about right triangle trigonometry. Let's suppose you have a right triangle. It's horrible, but that works. And all you know are the lengths of the sides. You don't know any of the angles. Well, what do trig functions take as input? What do you input into sine, cosine, and tangent? Angles. Angles go into trig functions as input. What do they output? Ratios of sides, right? For example, sine, if I input an angle into sine, it'll output an opposite over hypotenuse ratio. Okay? Well, in this case, I don't know any angles to input into sine, and guess and check is just not going to work. So I need to use a function that can take that ratio of opposite to hypotenuse, plug that number in, and it'll tell me the angle, right? So you remember that in geometry? If I say the inverse sine of, in this case it was 4/5, right? It tells me 53.13 degrees. Perfect. Right? So inverse functions are used a whole lot in trigonometry to solve for angles. Used a whole lot in computer security. Here's an example. Let's say I need to talk to somebody securely. You can't really prevent people on the internet from being able to snoop in on your internet transactions. Okay? But what you can do is make sure that when you send the message that it's secure. So for example, I prepare my message that I want to send over the internet, and I take that message and I drop it into a special function that encrypts that into gibberish. And then what I send over the internet is just gibberish. So if anybody is reading it, I don't care if they have no idea what I'm saying. Then that message gets to the recipient. They have the inverse function that takes that gibberish and decrypts it into my original message. And you rely on the fact that these functions and inverse functions are secrets. Only I and the recipient have them, and hopefully anybody snooping in on the message cannot figure out what those functions and inverse functions are. Or, actually, more realistically, there are ways for them to be able to figure out what the functions are. It just takes a couple centuries before they create them, and by then, hopefully, your message is no longer, the privacy of the message is no longer a big deal. Another way the concept of inverse functions is used is something we call hashing algorithms. So let's suppose I go to a website and I type in my password. Have you ever had a website that when you forget your password and you hit the little reset password button, they actually email you your password? Do many websites do that?
No.
No. Most of them make you reset the password. Do you know why they can't just email you your password? Because they probably don't actually have it. They don't know what it is. They never stored your password. What they do is they take your password when you create your account, they drop it into a function that turns it into gibberish, but this function is very, very special. It's special in that there is no inverse function for it. It's impossible. You cannot make an inverse function that will turn that gibberish back into your password. So once your password is turned into gibberish, nobody can ever decrypt it. So if their servers get hacked, people still don't know your password. Safe. Okay? So when you go to log into that website, they've got this gibberish stored on their servers. You type your password in, they immediately hash the password and get gibberish, and they compare the gibberish, make sure it matches. That's smart. Pretty cool. One of the most common gibberish functions, or hashing functions, is called MD5. Okay? So here's a website that will actually generate MD5 hashes for you. So let's try the MD5 hash for password. Oh, there it is, password. Or, there it went again. It's weird. So all of this gibberish right here, that is the MD5 hash for the word password, and it cannot be reversed. It can't. The government, because this is such a huge part of computer security, the government has actually established guidelines for what a hashing algorithm has to have. It cannot be reversible, so an inverse function cannot exist. For any input, the output has to be unique. So no matter what, every time I type password, I get that same exact hash. And there cannot be two different inputs that cause the same output. So that could be bad, right? I could potentially type in a password that's not actually my password, but if it creates the same gibberish, I get in. They don't want that. MD5 was recently found to be flawed. People found two different inputs that created the same output, but they were so big and giant and complicated that it was unlikely to ever actually happen. So it's actually still fairly secure. But the government has actually created SHA-1, SHA-256, and they are currently working on SHA-3, which is actually a challenge. The government said, hey, we want a new hashing algorithm that's more secure, and they sent it out to a challenge. And so there's all these different groups working on it now, and they're slowly whittling it down. Like, there were 5 still in the running, and then they went to a conference and presented their latest findings, and the government said, you 3 are the best right now. And so eventually they'll pick one. But even though it's not reversible, people still try, right? People still try. So what people have done is they have just stored a database full of ordered pairs, password and MD5 hash. So here's a website that has on file in its server databases 13 million MD5 hashes where they have just stored it. So you could potentially take an MD5 hash like this one, type it in here, and see if it's in the database. Yes, it actually is. So they're not actually inverting it. They just have that stored in there. So let's see. Let's see. Do they have that? Do you think that's one of the 13 million they have in there? No, no results. What's a common password people love to use?
Password 1.
Password 1. Is that your password? Love. Think that's one of the 13 million? Yep. This one's interesting. Candy. Think that's one of the 13 million? It is not. What? Are you kidding me? 13 million and candy isn't one of them? It just blows my mind. That's my password. But 13 million seems like a lot, but the reality is that's not a lot, you know. How many of you think you have a password that's in that database? No, you guys use secure passwords? Good. That's good. You know, password security is still a funny thing. A lot of people think they can make a password secure just by mixing letters, punctuation, numbers, and all this gibberish. Has anybody ever heard of XKCD? They had a funny one about password strength. So here's the password: capital T R 0 UB 4 DOR ampersand 3. Right? If you had a computer that could guess passwords 1,000 guesses per second, that password would be guessed in 3 days. Whereas if you instead picked 4 dictionary words, just 4 dictionary words, correct, horse, battery, staple. At 1,000 guesses a second, it would take 550 years to guess that password. And it's easier to remember because you picture a horse saying, that's a battery staple. Hey, correct. It's hilarious. You'll never forget it. This poor guy, can't remember. Was it trombone, troubadour, was it a 0? I have no idea. That's fascinating to me. Easier to remember, way harder to guess. 4 dictionary words. I don't follow that. I use the same password I've used since I was in like 9th grade. Okay. So let's get back to inverse functions. So we've got our function f, we've got the function f inverse. Here's another cool property of inverse functions. If I were to compose these 2 functions together, create a new composite function, we end up with the most boring function in the world. If 3 goes in as the input, what comes out? 3. If negative pi goes in as an input, what comes out? Negative pi. We call it an identity function. Whatever the input is, the output is the same exact thing. Will that always be true for inverse functions? Yes, always, right? Because whatever f does to the input, f inverse just does the opposite. So you're guaranteed it goes straight through, okay? The same thing is true if you compose them in the other direction. Whatever the input was, f of x, comes right out, f of x, okay? And it has to be true in both directions. And so, in fact, that is actually the definition of inverse functions. If you've got functions f and g, and when you compose them together, you get x, and when you compose them together in the other direction, you get x, then they are, in fact, inverse functions. That's the rule.
How is it possible that when you do a composition, one inputs x, but the reverse does?
I'll show you. It'll blow your mind. You sure you can handle it? Yeah, we'll look at an example of that. Okay, ready to do some examples? We're going to start with a more basic example. Okay? Show that these 2 functions are inverses. I'm not asking you to determine if they are. I'm asking you to prove it. So that should change your entire mindset for how you do this problem, more importantly, how you show work for it. The proof. Not that 2-column crap. That's not real. I don't know why we do that. Why do we do 2-column proofs? You know what I hate about 2-column proofs? like, nowadays, teachers are, like, really, really generous, and they give you the columns, and they say, like, yeah, this should take 8 rows. And, like, students would come into math lab with geometry help, and I'll be trying to do this proof, and I can do it in 7 or 9 steps. I cannot do the thing in 8. And then 8, like, right there, and I just can't stand it. Anyway. I'll tell you what, before we go and prove these functions are inverses, real quick, let me just make up 2 random functions here. What do you think? Think those might be inverses of each other? 2x squared minus 3 and x plus 13? No, probably not. So let's prove that they are not. How can I prove these functions are not inverses of each other, Drew?
Plug the same number in both vector graphs.
Ah, that's for you, the first person all day that's went straight to the fast method. I love it. Very good. Ultimately, could I compose them together and show that they don't simplify down to x? Yes, you can. That is valid. That is great. But I think there's a faster method. Pick a number, any number. Somebody give me a number.
Yeah.
I heard 7. Plug it in. F of 7. 2 times 7 squared minus 3. That's 2 times 49, 98 minus 3. So this outputs 95. So that is the ordered pair. Input 7, output 95. If these are truly inverses, then what should happen? If I plug 95 into G, what should it output? And it definitely does not. So they're not inverses. One single example is enough to prove that they are not inverses of each other. Just one. We call it a counterexample. That is a proof by counterexample. Okay? Clearly not inverses of each other. Okay? So if I can prove functions aren't inverses by counterexample, can I prove functions are inverses by example? Right? Could I come up here and like plug 2 in and I get something like 2 comma 15 and then plug 15 in here and get 15 2? Is that a proof that they are inverses? It's a proof that for that particular input-output pair, they are inverses, but you're going to have to prove it for all of the other potential input-output pairs, which is how many? Yeah, infinitely many. I would not recommend attempting that. So you can't prove something by example unless there's a clear, reasonable, finite number of examples. So instead, the only way you can prove they are inverse functions is by composing them together. So we do F compose G, what happens between the cube and the cube root? Cancel. Whoa, why did I write a 3 down there? What is wrong with me? What happens between the 2 and the 2? And then the 1s cancel, and we end up with x. That's great. Is that enough right there? Can we stop? Are they inverses? No. You have to do the other way as well. G of f of x, cube root of 2x cubed minus 1 plus 1 over 2. Now, this is a perfect example of, this is a proof. It's all about your work, not the end result. You already know these are inverse functions. You already know this is going to simplify down to x, right? So if you do something like, yeah, blah, 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 that simplifies down to x. No. You're going to miss points. And if you do something like this, oh yeah, look at this, the 1's cancel, the 2's cancel, the cube's cancel, the cube root x, we're done, we're great. Okay? Because you don't know how often people will actually simplify this wrong. They'll cancel the 2's before they cancel the 1's. Or they'll cancel the cube and the cube root right off the bat. You know, you still have to correctly show me that you know how this simplifies, especially early in the year. So the 1's cancel first, then the 2's. What is that? What is wrong with my hand? Can't write. And then the cube cancels the cube root and you end up with x. Okay? Really show all of that work. I know what the end answer is going to be. You know what it's going to be. Show the correct simplification. Make sense? So I guess there's a question. So the question was, why do we have to show them in both directions? Well, here's a perfect example. What function in our calculator clearly has an inverse function also in our calculator? Sine, cosine, tangent. So let's look at sine. Let's take the sine of the inverse sine, and somebody just blurt out a number. 4 won't work.
14.
None of those will work. Okay, let's think about this. Sine is the ratio of opposite to hypotenuse. Opposite over hypotenuse. Which one of those is guaranteed to be bigger? The bottom. So therefore, can you have an opposite over hypotenuse of 4? 0.25. Sounds great. If you type 4, you'll get an error. Your calculator will give you an error. 4 is not in the domain of inverse sine. But 0.25 is. So guess what? When I hit enter, what's the calculator going to output? 0.25 is perfect. Was that a surprise? No. Let's do the inverse sine of sine. I'll just blurt out a number.
What?
I heard 105. I hit enter. What are we going to see as an output? What? What? What does that mean? Sine and inverse sine are not actually truly inverse functions. Isn't that crazy? Doesn't it blow your mind? It blows my mind, and I've known about it for years. They're not. They're not truly inverse functions. Sine actually doesn't. We're going to jump in ahead of ourselves. We'll talk about this tomorrow. But how do you determine when looking at a function if its inverse is also a function or not? Do you remember? Horizontal line test. Sine fails the horizontal line test miserably, infinitely many times. So therefore, sine does not have an inverse that passes the vertical line test. So what we do is we chop sine up into just a little portion that does pass the horizontal line test, and then we take the inverse of that, and it's just the best we can do. So inverse sine is the best we can do. It's good enough. It helps us solve problems. But because sine doesn't have a true inverse function, it requires we still use our brain when we solve triangles and stuff like that. In fact, inverse sine can never output an obtuse angle. So how in the world do you solve a triangle that has an obtuse angle? Right? You've got to use your brain. The calculator's not going to be able to do it. That is a combination of brain and calculator. Isn't that wild? Now, if I type a number less than 90, like 73, yeah, that works. Works just fine. Okay, we'll learn about all that later when we learn trig. Let's do another one. What's the inverse of x squared? Square root of x. Let's prove these are inverses of each other. So we compose them together. F of g of x. What is the square root of x squared? Square cancels the square root, we get x. Halfway there. G of f of x. What is the square root of x squared? Square root, square cancels, we end up with x. So we have proven they're inverses, yeah? No, that is wrong. For example, somebody give me a negative number. -3. When I plug -3 into x squared, what does it output? So therefore, when I plug 9 into this, it outputs -3, right? No. It's not plus or minus. This is good. This is good. Okay, let's have a discussion about that. This has happened every period. This is perfect. How many square roots does the number 9 have? It has 2. How many tenth roots
does the number 1024 have? 10. There are 10 numbers you can raise to the 10th power and get 1024. 8 of them are imaginary, but there are 10. But when I say this, when I say radical 9, what is the answer? Just 3, not plus or minus 3, just 3. When I say 10th root of 1024 with a radical, what is the answer? Just positive 2, not negative 2, not blah, 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 plus blah, 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 I, or whatever some of the imaginary roots are. The radical notation only means the positive real root. So even though there are more square roots, more cube roots, more fourth roots, when using a radical, you only are talking about the positive real one. So when we go back up here, there's no plus or minus involved. It's just radical x. So when 9 goes in, what is radical 9? Just 3. Just 3, right? Here's another question. Is radical x a function? Radical x is a function. For each input, there's only one output. When 9 goes in, what comes out? 3. Not 3 and negative 3, right? It's a function. So, 9 goes in, positive 3 comes out, not inverses. But the work I did in blue looks perfect. Where is my mistake? What work did I do there that was wrong? And I blame your Algebra 2 books for this. They're too easy. What is the square root of x squared? Not plus or minus. When do plus or minuses come into effect? If I give you the equation x squared plus x squared equals 9, what is the answer? Plus or minus 3. Okay? But if the radical is already involved, and there's not a plus or minus in front of the radical, there's no plus or minus. What is the square root of x squared? Pick a number, any number. 7. What's 7 squared? The square root of 49. 7. What went in came out. That's great. Give me another number. Negative 7. What's negative 7 squared? 49. What's the square root of 49? 7. Clearly, the x going in was not the x that came out. So simplifying the square root of x squared down to just x is wrong. The square root of x squared is not x. It's absolute value of x. How many of you went through all of Algebra 2 simplifying radicals and just saying the square root of x squared is x? Do you know why you did that? If you go back to your Algebra 2 book and look closely, every single homework problem said, simplify the following radicals. Assume all variables are positive. Well, if the variables are positive, what's the point in writing absolute value bars? If you know x is a positive number, what's the absolute value of x? It's just x. Well, that's not the case here, is it? So we got to be really careful about that bad habit. We got to really look into that. So these functions are not inverses of each other. Simplified down to x here is not simplified down to x here. They're not inverses of each other. But one of the things we like to do, how can I modify f of x? Clearly fails the horizontal line test, right? How can I modify it so now it does have an inverse that is a function? How can I restrict its domain so that these are, in fact, inverses of each other? Restrict the domain to only x's greater than or equal to 0. Okay? Now when I compose them together, f of g of x, that is the square root of x squared. That still simplifies down to x. That's great. Now when I do g of f of x, I get the square root of x squared, which we just learned is the absolute value of x.
But, isn't x only going to be a number greater than or equal to 0? So what is the absolute value of x if x is guaranteed to be not negative?
It's just x. There. Those are inverses of each other.
So again, something you learned in algebra 2 and was easy is actually more complicated than you thought because of what concept? Domain.
Okay? Good stuff? Make sense? Learn something today? Good. Anybody's mind's blown? No? That's good. You're all lying. I see the scheme. Why are we looking at Jessica? That's all I want to do today. Here's the homework. You can definitely start it. You won't be able to finish it. That is every other odd, E-O-O. It's only like 20-some problems. Don't freak out. Every other odd. So 9, 13, 17, 21. I don't know if 101 is where you stop or not. You might stop at 99. If you get to number 99, don't think like, oh, I messed up my order. I better go back and do all the other odds. Then you just end up doing way too many problems.